Alright, so let's start recording now. Open up the window. Okay. So we should talk about the final exam and do a bit of review for that. Okay? If you need help or demoing stuff, I can assist or facilitate that. Feel free to reach out to others. I mean, that's why the Discord channel is there. Alright. So, with regards to the final exam, I'm going to open it on my other screen. Just simply to make sure I can look at it. Okay. So, let me go through what you should expect on a final exam. Can everybody hear me, by the way?
Yes.
Okay.
Yep.
Final exam. All right. So we've got our. So you'll have 3 questions of choose the right data structure. Okay. You know, just like you did on exam 2. Then you'll have a question on quicksort, which will ask you to do partition once. Okay? So given an array, tell me what happens after you do the partition algorithm to it once. In other words, sort the array, run quicksort right before it recurses. All right? There will be a question on hash tables, and I will go over questions that are very similar to that, but it simply said, given a key, show me that you know how to put things in the right place with, given a hash function and given the key and these indices, show me that you know how to put it in the proper index.
Hey, Prof, are you recording this?
Yes, I am.
Okay, thank you.
So let's talk about my graph questions. My graph questions are fairly straightforward. One of them is, but what I'll do is that because drawing a graph is a pain, for me, I'm just going to give you I'll give you either an adjacency list or an adjacency matrix. And then you need to be able to recreate the graph from that so that you can do your breadth first search or depth first search. You don't have to draw the graph for for the answer, but the graph is not in a picture form. It's either in the adjacency list format or the adjacency list or adjacency matrix format, and you have to use that to solve the problem. And then you'll use that also to do Dijkstras. So you'll have to do BFS or DFS and Dijkstras on a graph. And those will be the non-coding questions. So for the coding questions, I will be giving you a tree, and then I'm going to ask you some questions about that tree, some true-false questions about that tree, and then I'm going to ask you to write an algorithm that uses that tree. Then there will be a linked list question, and then there will be a hash map question. And that's it. So 1 question on trees, 1 question on linked lists, and 1 question on hash maps. So, other questions about the final exam. And I'm going to go over I'm about to go over a practice exam with you. Okay?
Is the Huffman coding thing?
Nope.
Okay.
I mean, it normally is, but when I moved to online, it was really I didn't have the chance to generate questions for them, and with the accelerated summer semester, I feel like that's okay to cut, since it's not necessarily taught in all data structure classes. It's more important that you got the graph stuff in and the sorting stuff in. Other questions? So, to reiterate, 3 questions. Choose the appropriate data structure. A question on a multiple choice question about quicksort where I'm going to ask you, hey, which of these follows the directions that I gave you? You'll have a question about, then you'll have a short answer
Sorry,
question.
I just got here. Where's the file? Is it?
No,
Is it? Which file are we looking at?
nothing yet. I'm actually telling you what's going to be on the exam right now.
Okay.
And then I'll share my screen.
Okay.
All right. So first off, we have as I said, we have 3 questions of choose the right data structure, 1 question on quicksort. Then question 5 is a short answer question about sorting algorithms in general. Question 6 is hash table. Show me that you can perform open addressing. Show me that you know how hash tables add stuff using open addressing with linear probing. A question on
Is that one coding or a short answer?
It's a auto-graded. It's a special multiple choice question. It involves dragging and dropping.
Okay.
Question 7 is a multiple choice. Here's a graph. Do DFS or BFS on it, and the graph is not going to be a picture. It's going to be in adjacency list or adjacency matrix format. The next question will be, hey, that above graph, you know you did BFF or DFS on it? Well, now you're going to do Dijkstras on it. Okay, and all those questions together is about 50 points. Okay? So you've got 8 questions in the non-programming section, okay? And then for the other section, you have 3 questions. For the programming questions, you have about 3 questions. There's the... So what I have is I have 1 question where I give you a new tree with new rules, okay? And then I ask you to write I ask you some true-false questions about that. Like 2 true-false questions saying, hey, does this tree follow the rules? Okay?
Okay.
And then the next question after that is, here's the new tree, please write me an algorithm that does something for it. Right? Then I have a question that will concern itself with linked lists, although you don't have to know how to use the nodes. Okay? Like, you want to use linked list methods. Okay? And next is, and then the last question will be on hash maps. And it'll be unlike anything you've done before, but I explained the problem in pretty good detail. And it's not an uncommon problem. Alright, so first off, let me go ahead and show you a couple things. So let me go to GitHub. Always found that so here's my classroom code. If I go to destruct over here, you'll notice that there is a study guide over here that I made 3 years ago. Which here are the programming topics to review. And then at the end, you'll need to download this document where I have links to other final exams, one of which we'll go over today. Okay? So these are final exams from other institutions, or example finals. This one is personally my favorite, which is the Practice Computer Science final from Harvard. I find it to be I have very, very good questions, so that is the one I'm going to go over, if that's what people would like to do.
If you think that's the most useful one.
It is very thorough in the amount of things to go over. It's not necessarily and it covers a lot of the same topics, even if the questions aren't the same. So, So, okay. Let's go ahead and review. Okay, and I'm going to make use of the annotation function of a lot of annotating. Okay, when in doubt, use pencil and paper. By the way, don't try to solve problems in your head. Question number one is a great example of that. Suppose you have items A, B, C, D, and E are pushed in that order onto an initially empty stack S. We then pop S 4 times, and as each item is popped off, it gets inserted into a queue. So if 2 items are then removed from the queue, what is the next item to be removed from the queue? Right? Kind of makes your head a bit dizzy thinking about all that, but let's think about that. A, B, C, D, and E are pushed in that order onto an initially empty stack. Right? So let's go ahead and make the stack A, B, C, D, E. Right? Okay, onto an initially empty stack, and then that stack is popped 4 times, and as each item is popped off, it's inserted into an initially empty queue. So we've got a queue here. E, D, C, B. Right? Makes sense what I just did there with the queue. Well, actually that arrow doesn't really make sense. Stack. Here's our stack. Yep, I've made it so it's going to play more laser. Alright.
You have 2 Bs, though.
Yep, I just noticed that. We've got to erase. Alright, now it says, we've popped them into there. Now it says, if 2 items are removed from the queue, okay, 1, 2, what is the next item to be removed from the queue? And the answer is C. Okay? Makes sense?
Mm-hmm.
Alright, clear all. Okay. If the binary tree below is printed in pre-order traversal, what will that result be? So why don't we go ahead and just do pre-order traversal, which means handle myself. So it's got to start with 6, so A and B are out. Then handle my left child, and then handle my right child. So C is out. I don't know what it's doing there. 6, 9, 6, 9, 17. It's not even a binary search tree. So that's possibly what throws some people. But it's just a binary tree. So 6, then we go to the left side, which says handle myself, then handle my left and my right. So then 9, so it looks like E is the answer, because we'll go to 6, then 17, then 9, then 4, then we go to 22, then we go to 16, and then we go to 12, right? Handle myself, handle my left children, then handle my right subtree. So 17 goes, okay, handle myself, handle my left subtree, then handle my right subtree, which is 9 and 4. Make sense to everybody?
Yep.
All right. A graph implementation that uses a 2D array to represent the edges would be most reasonable in which of the following cases? 1,000 nodes, 12,000 edges, 100 nodes versus 4,000 edges, 1,000 nodes, 10,000 edges, 10 nodes, 20 edges, and none of these, since a graph can be represented only by a linked structure. So, first off, is E correct?
No.
No. What are the 2 ways you can represent a graph that we've learned?
As a linked structure or as an array.
Right. So we can use an adjacency list or an adjacency matrix. Right? So when do we want to use one over the other? Why do we have 2 representations of it? Why do we use 2 representations anyway?
Isn't it based on how full the graph is?
And what special terms do we use for that?
I can't remember.
Sparse and dense.
Yes.
Right? We have sparse graphs and we have dense graphs. Sparse graphs are where there aren't too many, where basically the number of edges and the number of nodes, are roughly the same. Okay? Whereas a dense graph approaches says, babe, there's close to n squared edges. Right? Where there's, so this is a more dense graph where basically it's closer to n squared. Okay, and adjacency lists are better for sparse graphs because with an adjacency matrix, right, which will look something like this, right, we have nodes A, B, C, D. Let's go ahead and I'm going to just create a graph and create the adjacency matrix for it. A, B, C, D. Okay, here's my graph. Note that it has only one edge in it. Okay. We have only one edge. So we have an edge from A to B, so we'll put a 1 here, and there's zeros, and there's basically nulls or zeros in all the rest of the cells.
Except for the BA.
BA. Yep. Well, if it's an undirected graph, I can be even cleverer and say we don't need to store this stuff, the lower diagonal. But anyway, but yeah, that's a waste of space right there. Whereas for a data structure, for a link structure, we would basically say, okay, we'd have a map that says here's the key A, the value is B, B, A is linked to A, C is linked to nothing, and D is linked to nothing. So, nothing. So, very little wasted space there. So, does anybody remember what the magical cutoff point is for what percent of possible edges that need to exist that we decide to use sparse over dense? Answer is about 25% of all possible edges need to be filled. So if you could fill a adjacency matrix with so if you could fill a quarter of the adjacency matrix's cells, then you want to use an adjacency matrix over an adjacency list. That's kind of the cutoff point there. So let's take a look at this. With A, there's 1,000 nodes and 1,200 edges. But how many possible edges are there? There's 1,000,000 possible edges, right? Does that make sense to everybody? Did I lose people?
That makes sense.
Yep, there's 1,000,000 possible edges because there's 1,000,000 possible source destination combinations, including A to A, B to B, C to C, D to D, and all the other ones. Okay? So what is 12? So 12,000 over... Well, that's just... We can just straight up say that's less than 25... That's less than 0.25, right? So we can kind of rule this guy out. Okay? Make sense?
Yep.
Now we've got 100 nodes and 40 edges. 100 nodes...
4,000.
Sorry, 1,000... Yeah. 100 nodes versus 4,000 edges. So 100 nodes squared is 10,000 out of 4,000. Shoop. Shoop. 4 out of 10, which is 0.4. So this is a cool one. That would be a good one to use. Here we have 1,000 nodes, 10,000 edges. Well, 10,000 is a lot. 10,000 out of 1,000,000 is 1%.
Not a lot.
It's 1%. So, no. And now, over here, D is pretty close, but it's not as close as well because 20 edges out of a possible 100. So, it's most reasonable to use it for this guy because he's got 0.4. Right, so D is our... So B is our correct answer. Clear all drawings. Mouse. Scroll down. A binary tree is constructed of nodes with... So they didn't use generics. So they just have a node that holds an integer and a left and right. Consider the following method. Public static node mystery, which takes in a root node. And if root.right is equal to node, return the root.
You mean null?
Sorry, root.right is equal to node.
Null?
Yeah. If root.right is equal to null, return root. Otherwise, return a mystery root.right. So we hire 3 consultants, and we get following 3 opinions about what the method does when it's passed a reference to the root of the whole binary tree. Okay? Consultant 1 says it returns the last node visited in order traversal. Consultant 2 says it will return the last node visited by post-order traversal. And the third consultant says it will return the last node visited by a level order traversal, which is just breadth first search. Okay? In other words, it will return the last node in a BFS. So which of these opinions is correct regardless of what the contents of the tree is? So let's take a look at what this will do. Right? If root is... We really only care about the right side, so... Right? We call it on this guy. If root is...
Well, it can't be D, because those would be different things.
Maybe. We'll see.
Sorry, I misread that. I was thinking that said 1 and 2.
Let's go ahead and... So let's go ahead and see what this will be. Okay? So we've got root.right is equal to null. So this isn't the case. So return mystery root.right. So we call mystery root.right, which calls mystery root.right, which calls mystery root.right all the way down until we get to the very end. Which will then say it will return itself to its parent, which will turn that. So it returns this node over here. It returns the rightmost node. Okay? Does that make sense to everybody that this returns the rightmost node?
Mm-hmm.
So now let's think about this. In an in-order traversal, the rightmost node is going to be the one... In an order traversal, we'll go through and it's going to handle all those stuff on the left, then myself, then all the stuff in my right subtree, and do so recursively. So if you think about it as a binary search tree, the rightmost node is going to be the greatest item, the largest item in the list. Largest item in the tree, right? Which is the last item returned by a in-order traversal, right?
Mm-hmm.
So consultant 1 is correct. It will return the last node visited by an in-order traversal. I cannot falsify this. So let's try to falsify number 2. It returns the last node visited by a post-order traversal. Pretty easy to do. A, B, C. The last node visited by the in-order traversal is going to be A. Sorry, by a post-order traversal is going to be A. Right? Handle my left subtree, handle my right subtree, handle myself, right? So B cannot be correct because the last node visited would be A, but this will return C, but mystery returns C. Does that make sense to everybody?
Mm-hmm.
Finally, last node visited by level order, right? It appears on the first glance that that would be the case. Right? If we do a level order traversal, so if we create a binary tree, it'll return the last node in the level order traversal. Return this guy, right? But if we just add a node right over here, boom. Level order traversal or breadth first search, this would be the last node in a breadth first search. Right?
Mm-hmm.
So B would be incorrect. So number 3 would be incorrect. So the correct answer is A, 1 only. Make sense?
And they should consider not hiring consultant 2 ever again.
Right. All right. So, with a poorly chosen hash function, it is possible to have a situation in which the search time in a hash table of n items goes to what? So what is an example of a bad hash function? H of x is equal to... What's a good example of a poorly chosen hash function?
Okay, here's h of x equals 1.
Yeah, I was going to do h of x is equal to 0, my personal opinion. So this would hash everything to index 0. Meaning every node is going to be inserted into the same index. Or every key is going to be inserted into the same index. So what would the run type for that be?
That would be O of n, right?
That is correct. O of n. Because we'd insert the first item, it'd go in correctly. And then we'd get a collision, and so we'd put in the second place. Then the next item would have 1 collision, 2 collision, and put it in the next place. The third one would go 1, 2, 3, and go into the end. So basically, we would just we would iterate through all the items and tack it onto the end, where n is the number of items. It would not be n factorial because that would be impressive. Log n and n squared, and constant time is what we want. So, all right, I'm going to skip this because you did this one in your first exam. All right.
Oh, that's the exact same one, too.
Well, not the exact same one, but it's structured very similarly. They ask for which of these is not the third node in the list. So, I asked, here's a bigger list. Which of the nodes does this resolve to? Alright, so a police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets so it can be determined very quickly whether or not a given license plate number is in the database. The speed of the response from the database is very important. An efficient use of memory is also important, but not as important as speed of response. So if you've got, in other words, if you've got two things that will be just as fast, then ERF are the one that's going to use less memory. So which of the following data structures would be most appropriate for this task? A sorted linked list, a sorted array with 1,800 entries, a hash table with open addressing with 1,800 entries, a table size of 1,800, open addressing with 3,600, and open addressing with 10,000. All right, let's look through these and figure out how much memory and how much space is going to be, how much memory and how much speed are you going to use. So how long does it take to search for would it take to search for an item in a sorted linked list? The answer is obnoxiously long, actually.
Yes.
So I would go with either the answer is, I think, probably n log n time to search for something in a sorted linked list, because to do a binary search, you'd have to sort in the middle. In fact, you'd be better off just doing a linear search and finding it in O of n time. So the most efficient thing you can do to find something in a sorted linked list is to iterate through everything, because you can't get to the middle in constant time, which means you can't do binary search. So this takes O of n time. That's no bueno. A sorted array with 1,800 entries. So how quickly can we search a sorted array for something?
Wouldn't that also be O of n?
It's a sorted array, which makes all the difference in the world.
Oh, yes, log n.
Log n, which lets us use binary search. Right? Because we can search in the middle, and we can look at the middle item and say, is it less than or greater than, and cut half the items out of our search. In terms of memory usage, this is the best memory usage we can get, because it's just using an array. Okay? And if we're using an array, then we're going to be using them, and if we just wanted to basically balance speed and our memory usage, the array would be best, but we want speed to be the most important thing. So now if we used an open, if we had an open addressing table, a hash table with 1,800 entries, how long would it take to search for something in there? We have 1,800 license plate numbers stored in there, and the table size is 1,800. How long is it going to take to find an arbitrary item in there?
It's going to be close to O of n.
Right. In other words, the question to ask yourself is, how long would it take to find my car if I can't remember where I parked and the parking lot is full? Or, alternatively, how long does it take me to find an empty parking space when there's only one parking space left? And the answer is, it takes freaking forever. Right?
Yep, it does.
So, yeah,
Although at the Philly airport, they do have those monitors saying how many open parking spots are in each section of the parking lot.
Yeah. But all right. But now we've got we've got a hash table using open addressing with 3,600 entries. How long is this going to take?
That's going to be very close to constant time.
Right. The expected according to Knuth, the expected number of lookups the expected number of lookups should be about, with a hash table of size n, is 1 plus the 1 over 1 minus the L. Does anybody remember this formula from the slides in the videos
Yep.
I did?
Yep.
And L here is the load factor, which is the percentage of things that are filled up. So if it's, in this case, the load factor here would be 1/2, right? 1,800 with 3,600. And so let's just do some really quick annoying math. So half the way filled up, which means that this becomes 1 over 1/2, which is 2. And so the answer to this is it takes 3 expected lookups, or 2 expected collisions, I think. I think that's the formula. It's either 1 over...
No, that looks right.
Okay. Now, so 2 expected lookups, that's great. And here we're using 50% memory overhead. So 50% of our spaces are wasted, right?
Yep.
Now we have a hash table with 1,800 entries. Okay, so let's do the same formula. 1 plus 1 over 1 plus 1,800 over 10,000. Except, here's the thing, I hate math. And
let's just round it up to 2,000.
Yep. So in computer science, it's a very useful skill to do the very quick and dirty approximations. So here that would be
1/5.
So that will be 1/5. So 1/5. So 1 plus 1 over 5. Oh yeah, I made a math mistake. It should have been. Was it 1 plus 1 over, or was it 1 minus 1? I think it was minus.
Oh yeah, that one is a minus.
So it should be minus 1/5. So this will become 4/5, which will become
5/4.
5/4, which means the expected number of lookups should be. I feel dumb like I'm doing this. So that should be 1 plus 5/4, so 2 1/4 lookups. So 2 expected lookups with a 25% chance of having 1 more, let's say. Okay? So that's 3 lookups versus 2 and a bit. Right? Very exact math terms here, right? But here we're wasting approximately 80% of our space. So at least if I was the one giving the exam, I'd say D is the answer because these are both constant time lookups, right?
Yep.
And there's really no difference between 3 and 2 and a bit, in my opinion. You feeling better, Annie?
I'm awake now.
Yep. I highly recommend caffeine. You see this weather? Awful. All right, so...
Good for my plants, though.
Yeah. So, Huffman trees we don't need to go over right now. An array of 7 integers is being sorted by the heap sort algorithm. So, after the initial phase of the array, which is constructing the heapify method, which of the following is the possible ordering for the array? This is actually not a sorting question, this is a heap question. Because the heapify turns this into a max heap, right? So basically it's asking, which is a possible ordering for the array? In other words, which of these is a max heap? So A is 85, 78, 45, 51, 53, 47, 49. So
I think it's B.
So is this a max heap over here?
No.
No, because if we look at 45, 45 is not the biggest thing in its subheap. 85, 49, 78, 45, 47, 51, 53. So it looks like B is a correct answer. Okay? Let's go ahead and look at the other ones, though, just to be sure. 85, 78, 49, 45, 47, 51. Oh, we can stop here because 51 is bigger than 49, so it should be on top. And then I can actually just look over here, give a glance over here. This 45 is not the biggest item in the entire thing, so nope. And then 85, its children is bigger than its children. Is 51 bigger than its children, which is 51 and 53 and 49? Nope. So E is not it. Okay. So the answer is B. And a binary search tree shown below was constructed using constructed by inserting a sequence of an array. We don't need to go over this one. You just did something like this. Similarly, I'm going to skip these because they are not really relevant. I'm going to make sure I can get these. You just did this, which is create a binary search tree. So let's look at this part. This is very similar to what you'll have on the exam. You're given an empty hash table of size 7 that uses open addressing. The following sequence of keys are to be inserted: 15, 17, 8, 23, 3, 5. Insert each of these keys using the following approaches. If an overflow occurs, say so and indicate the item that causes the overflow. Okay, so here the hash function is take the key, mod it by 7, and resolve collisions using linear probing. Does that make sense to everybody? If it doesn't, watch what happens as I do the first couple. 15 mod 7. What is 15 mod 7? Well, fortunately, you've got calculators accessible, but I, don't need that.
1, right?
Right, it's 1. Divide it, keep subtracting 7 until you can't subtract 7 anymore, and you'll end up with 1. So 15 is going to go into index 1. Because that's what the algorithm says. It goes into index X mod 7. 17 mod 7 is 3. So 17 is going to go into index 3. Make sense so far?
Mm-hmm.
8 is going to go into 8 mod 7, which gives us 1. So we'd put an 8 here, but that space is already taken. So I'm going to indicate there's a collision and draw an 8 over here. Make sense?
Yep.
Next, we've got 23. 23, the closest multiple of 7 to that is 21. So 23 minus 21, 21 minus 20, 23 minus 21 is 2. So 23 mod 7 is 2. So we want to put 23 here, but we can't, so it's taken, so we look for the next possible space, which is 3, but that's taken, so we look for the next possible space, which is over here. So 23 goes over here. Now 3 mod 7 goes to index 3. So we'd want to put 3 here, but we can't. So we put in index 4, but we can't. So we put in that. So 3, 4, can't. So we put in index 5. And now 5, we try to put here, but we can't. So we put it into index 6. That makes sense to everybody?
Yep.
So on the exam, all I'm going to care about is, can you put the proper number in the proper index? And you'll just be dragging and dropping them into the proper index. Okay, what about quadratic probing? This was linear probing. Well, quadratic probing would start out the same. 15, 17, and then we'd try to put 8 in here. Right? So there's a collision though. So 8 mod 7 is 1. Try to put it here. So we look 1 squared away. We look at the space 1 squared away, which is over here. Next, we look at 23. 23 mod 7 is 2. We try to put it here. We can't. So we try 1 square away. 1 squared away does not work. So now we need to look at 2 squared away from the original space. So 2 squared away, which is 4. So 4 away from 2 is... So 1, 2, 3, 4. So we try index 6, which is empty. So we're going to put 23 in index 6. Right? With quadratic probing, you look 1 squared away, then 2 squared, then 3 squared. But this makes this actually quite easier to do this one. For index 3, we look 1 squared away. And for index 5, that just slots into 5, no problem. There's a lot of different hashing algorithms out there, or collision resolving. Here we have double hashing, which says, okay, so let's solve this doing, let's do this like we normally would for the other. So 15 goes here, 17 goes here, okay? And then we try to put 8 over here, right? But we can't put an 8 here because it's already taken. So instead we use the other one, the other hashing algorithm, which is x divided by 7. So 8 divided by 7 gives us 1, plus 1 gives us index 2. So we put the 8 over here. 23. 23 tries to go into index 2, right? So instead, what we're going to try to do with 23 is do x divided by 7, which is 23 divided by 7 is 3. Plus 1 gives us 4, so we'll put 23 over here. So that's what double hashing is.
What is the overflow?
I'm not sure. Honestly, I might not have done that correctly. I can't remember if you hash your hash after that, but that doesn't seem to make sense. But
yeah, especially because it would always be less than 7.
Yeah, so
the second hash would always be 1.
Yep. So what we would do here is there's also other hashing algorithms such as Cuckoo Hashing, which takes a completely different approach, named after the cuckoo bird, which will kick birds out of the nest. So if my space is taken,
love Cocoa Puffs.
So if my space is taken, get out of my space, use the second hashing function to resolve yourself. All right. So let's go over these graph algorithms over here. Okay. Here we've got we want to do a depth first traversal of the graph shown, starting with index C, with vertex C. Select the smallest edge when appropriate. Okay. Of course, you could just throw this into your editor, but here we're saying to break ties by using the smallest edge. So you would have to do some coding if you wanted to solve that. But so let's go ahead and we're going to start with C. To do depth first search, we're going to go from, and I'm just going to draw on here. So we're at C. we've got 3 possibilities to choose with as to where to go from C, right? Got B, E, F. And we're doing depth first search. And we choose the next place to go based off of the smallest edge. So we go next to B. Now we're currently at B, and with depth first search, we continue going with B because we're trying to go as deep as possible. We have 5 places to go. We're going to ignore one of them because we've seen that. We're going to ignore this one even though it's the smallest edge because we've just been there. So we have 18, 20, 17, 13. 13 is the smallest, so we travel along that edge to A. A has 2 edges, only one of which is relevant. D. And so then we're going to pop off. Right? We pop here because we have no new edges to explore. Pop off here because there's no new edges to explore. And now we're back to B. Okay? Where we have 2 more things to explore. What would be the next node to take?
F.
F. Because 18 versus 20. Gonna go here. F is a dead end because all of its connecting edges are places we've been. We're back at B. And then we go to E because that's the only other place we can go and visit. Pop off E, pop off B, C.
That looks like a 5.
What does? My E?
Yeah.
Okay, yeah.
Now it
E.
looks like a G.
Everybody's a critic. The pad is tiny compared to the strings or the screen, so me doing a small motion like this does a much bigger motion on the screen.
That's fair.
So now we are done. We've hit all 6 nodes. Now for breadth first search, that's actually even easier because we're just gonna go. We're just gonna go and explore the edges. We go through all of our neighbors in order. So C will go to B, E, and F, right? Because B has a 5. It's going to go to B first because smallest edge. Select the smallest edge first when appropriate. 22, 30. C, B, E, F. Okay. Is there anybody else I need to explore? Well, going from B, I would want to explore A and D. Well, actually, what I should do is say the best way to do that is B, E, F. So currently, so we're here. Next, let's go to B because that was the shortest edge. Okay, is there any place I can explore from B? And the answer is I can explore A and D. And I want to go to A first and then D. I'm done with B. I'm done with E. I'm done with F. A, there's nowhere else to explore. D, there's nowhere else to explore, so I'm done. Basically, you just radiate out. Right? Okay, suppose you're using Dijkstra's algorithm to find the shortest path. I'm just going to put the answer over there. Actually, suppose you're using Dijkstra's algorithm from... Actually, I'm going to zoom in and make use of this space to the side over here. Suppose you're using Dijkstra's algorithm to find the shortest path from D to E. List in the order which they become unknown, all vertices to which the shortest path is determined in the process, and the length of the shortest path. Right? So it's just saying do Dijkstra's. So let's go ahead and set up Dijkstra's algorithm, which is that we've got... Whoops. So I'm going to make myself a table here. Okay? Which is... we have our nodes A, B, C, D, E, and F. And our problem was to go from D. We want to find the shortest path from D to E. But to find the shortest path from D to anywhere to E, we have to find the shortest path from every node to every other node. Sorry, from D to every other node. So let's initialize this. infinity, 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 infinity. Initially, it's going to take, take forever to get to any other node from D is going to take infinite amount of work. Make sense?
Mm-hmm.
This is our distance. This is the previous node. Okay? So now, the first thing we do is initialize with the knowledge of starting with D, which is, we know there's a node from D to A, and we know there's a node from D to B, which have the following, things. Now, normally there's a V and a VS or something like that, two sets like that, but honestly, we can just use a check mark to say done. So, D to A is just 10, and D to B costs 17 units. So we're done with B, and now we can start Dijkstra's in full. Which is, to do Dijkstra's, we look through and ask, which is of these numbers is the smallest? Is 10, 17, infinity, infinity, or infinity?
I think it's infinity.
Depends on on which infinity we're talking about. So, I'm gonna go with 10. So we're gonna select 10, and now
A solid choice.
we are going to see and we're going to see what new information we can get. So A to B is the new edge that gets added here. And so we got to ask ourselves, does this give us a better route to B? So A to B is 13. So it costs 13 to get to B from A, which costs 10 in total. So we ask ourselves, is the cost to get to A plus the cost to get to the thing A is attached to, is that less than what we already know? If it is, update. Well, 23 is not less than 17, so there's nothing new to add. So we're done with A. What about B? So now let's check others. 17, infinity, infinity, infinity. Well, 17 is our next node. Oh, sorry, B is our next node because that's the smallest. So now let's see. We've got this edge over here. And B is going to connect us to CEF, which we can safely say is going to be less than infinity. So B to C, the cost is going to be a total of not 5, but 22. Right? The cost it took to get to B, plus the 5 it takes to get to C. For E, it's going to be a cost of 37. And the cost to get to F, 35. So we're done with B. Now let's look for the smallest one. The smallest one is C. So do we have any additional information? So it takes 22 to get from C to E. Is 22 plus 22, that's 44. That's not a better route. 22 plus 30 is not a better route to F. So we are done with C. And then E is done. B to E. E is done because because it can't get us to anywhere that's not outside of our known nodes. And same with F. So this is our answer. Personally, I think it's not the greatest for one for Dijkstra's. Now, one thing I do want to remind you is that Dijkstra's is a great shortest path algorithm, but it does fail in some cases. So for instance, if you want to find the shortest distance from S to Fien, which has a cost of 100, but then we've got A, B, C over here. Actually, we don't need C. We can just do let's see. 1, 1, minus 3. So if we do that, the shortest path from S to anywhere is actually
An infinite loop.
and negative infinite cost, because I can go so I can go from S to A, then A to B for a cost of 2, but then I get my cost back and then more by by traveling back to S. So this is where Dijkstra's fails here, as well as a lot of other shortest path algorithms. They'll fail in this case. Oh, Annie, Happy Feet needs food. She's out. These guys. So when you have a negative cycle like this, then Dijkstra's is going to fail.
What context is a negative weight on an edge valid?
Let's see. Like when you're, possibly if you're looking at fuel and possibly getting refueled, here's an example. Okay. Dollars to yen. 1.18. Now in this case, this is a homework assignment I got once, where basically suppose we have currencies, right? Right, and we can convert from one currency to another, right?
What's that last one?
New Israeli shekel.
Ah.
So so we basically suppose we're on the world market for currencies and we can trade currencies. Okay? How can we make an obscene amount of money? By the way, the weights are multiplicative and not additive, right? So we're looking at basically we can convert. If we start out with dollars, we would convert 1.18 of it to a yen. So, or we'd multiply that by 1.18. In other words, $1 is equal to 118 yen about. Okay? It fluctuates. But the idea here is that if you can find a cycle of some kind, say, where if you converted to dollars to yen to euros and back to dollars, and you ended up with just a teeny bit more than you started with, then that would be the shortest path for you in that case. And so you would want to do you'd want to maximize that trade as much as possible. Does that make sense?
Yep.
So it's not really negative weights, but negative weights do happen just simply when there's a cost. I mean, my personal example of a zero weight is going from Philadelphia to Camden across the Benjamin Franklin Bridge, right? So right, costs. If you take the toll, right, the toll bridge, $0 to get from Philadelphia to Camden, but $5 to get from Camden back to Philadelphia on the toll bridge. So not quite 0. So that's not negative, but it is 0. And it all depends on what your measurement is. And that's where you sometimes do get sparse, where you get multi-graphs, by the way, right? Typically, we've just been looking at graphs where you have A to B, right? But if there's multiple ways to get from A to B, then you can have multiple edges from A to B in a multi-graph. But most graphs don't really care about that. All right. Prim's algorithm and Kruskal's, those aren't things we really needed to cover, but they're in the book. They're for minimum spanning trees. All right. All right, complete enough. So let's take a look at this problem. This part of the exam deals with deals with binary tree. Here's the Java search method that uses recursion to search for a key in a binary search tree whose root node is referred to root, right? Here's the root. We're looking for the item, right? So rewrite the search method so that it uses iteration rather than recursion, it's saying. Easy enough to do. All right, so let's go ahead and try this one out. It's not really that bad. To use recursion is just a pain. We would just simply use a stack, specifically the runtime stack, to do our if we needed to do backtracking, but we don't. So right, what we're gonna do is first off, if root is equal to null, like we normally ask, we would return null, because we do have to account for the root being non-existent. Otherwise, here's what I do. While true, because I don't know what I need to put there yet. Node current is equal to root while current not equal to null. And actually, we can totally just put this over here and do return null. While current is not equal to null, if current dot key equals key, if current dot key is equal to key, then return current dot data. Else, if current dot key is less than, if the key we are looking for is less than where we're at, then current is equal to current dot left. Otherwise it's bigger, so current is equal to current dot right. And so that's how you do it without recursion. Which isn't that complicated. It's just a real pain to do if you're trying to do a balanced binary search tree and make it. On the other hand, this one I really like because it is recursive. So in fact, this one is really hard to do without recursion. Write a Java method called mirror that takes a reference to the root node of a binary tree and creates a new tree with its own nodes that is the mirror image of the original tree. We've used some variation of this as a question on our final exams before, by the way. Just FYI. I think like in 2016, 2017, we did something like a whole lot like this. So, takes a reference to the root node of a binary tree and creates a new tree with its own nodes that is a mirror image of the original tree. So, for example, if we pass this left one, so if we pass in what's on the left, then we'd get what's on the right. This is what would be returned. And the one on the right is a new tree. Make sense to everybody?
Mm-hmm.
So I'm going to use, because I prefer doing it the way that I would hope that you would do it, I'm going to use a node of ease. Right? So we're going to mirror. So the idea here is that, so first off, well, let's take a look at the case for the, let's just look at root case. Where do we start? Always start with, what if the root is nothing? If the root is null, what's the mirror of null? It's just null. Right? Otherwise, we need to make a new tree. Right? That's a mirror reflection of the left subtree and the right subtree, right?
Mm-hmm.
So node E new root is equal to new node root dot item, right? Taking the item, it's got to have its own copy of it, right? And then at the end of this, we're going to return new root because it's going to be the root of that tree or subtree. Make sense?
Yep.
So now we need to reflect the left and the right, which is pretty easy. I just need to swap my left tree and my left, from my perspective, right? One saying, hey, I just need to swap my left subtree with my right subtree, right? Right? 2 goes to where 3 is and 3 goes to where 2 is. But we also have to say, well, 2's children, 4 and 5, they get swapped as well. And 5 children, 6 and 7, they get swapped as well. But that's the problem for them. That's the problem from them. Right? First off, to be very clear about this, right? New root, my left child should be equal to the root's right child, right?
Yep.
And my right child should be equal to the original's left child. Except that that's pointing to the original ones. So instead what we're going to do is we're going to tell my left child to create a mirror image of yourself and your subtree. To create a mirror image of yourself. I'm going to tell my left subchild to create a mirror image of itself. Because mirror will return a new root. And that's it.
Yep.
When you can use recursion, it is these very complex methods that would get very messy otherwise become very easy to do. What is the big O time of mirror? Well, with trees, there's the you either are using a traversal or a zigzag, as I put it. If you're using a traversal, then you're touching every single node in the tree, which means the runtime is O of n time. If you're doing a zigzag, then you just are going left and right and cutting half the runtime out each time, so it would be log n. Here, we're mirroring every node, so the runtime would be O of n. It's a traversal method. All right, so let's go ahead. Do people want me to go over a few more problems before class ends?
I'm good.
You upload these study guide to campus,
Yep.
right? Awesome, thank you.
Mm-hmm. See. Link. So this one I think is a dead link, but you might be able to find it. Here's another one. Well, these are on the GitHub page in the study guide there. Ah! excellent question, because this touches on something we haven't done yet. So when you search for data structures and algorithms practice exams, by the way, you might get stuff like this, because data structures sometimes, what gets taught in algorithms and what gets taught in data structures gets sometimes mushy, depending on the exact curriculum of one school to another. So here, this focused on algorithms. So they're talking about big O versus big omega versus big theta. What are those, by the way? Anyone know?
Yep. Big omega is best case, big theta is average case.
Right. So big O says it's never going to be worse than this function. It's never going to look like, it's never going to, your runtime is never going to look better than something of this, of the order of magnitude of this function. Big theta says it's never going to look better than this. It's never going to go.
You mean omega?
Yeah, sorry, big omega is never going to look better than this. And big theta says it's never going to be better or worse. And mathematicians get very annoyed with us because a lot of times we use big O in place of big theta. Okay. So anyway, let's consider merge sort and insertion sort. Two algorithms near and dear to our hearts. For each algorithm, what is the worst case asymptomatic upper bound on the running
I think
time?
it's asymptotic upper.
Asymptomatic now. It's COVID. It's asymptotic upper bound on the runtime if you know additionally that A, the input is sorted, B, it's reversely sorted, and C, the input of size n, the list of size n has n copies of the same number. For each case in each sorting algorithm, state your answer and justify it with one sentence. So let's look at so first off, I can answer for merge sort. Case for ABC. It takes n log n because merge sort doesn't care. Merge sort will take your items. It will split it and split it and split it and then merge those splits together. It's going to do log n splits, and and each of those splits has to put together n items for a total of n log n. Doesn't matter what the contents is. Merge sort doesn't care. It's going to be n log n. It's consistent like that, and people appreciate consistency. It's a very valuable thing in this inconsistent world. So, now, what if the input is already... So, now let's look at insertion sort. What happens with insertion sort if we've got a sorted input?
I think that it would just be constant time, right?
Not constant.
No, sorry, not constant. Linear.
Yep, because we'd start with 2. We push 2 down to its appropriate space. It's there. 3 gets pushed down, which means it's there. 4, 5, 6. Each item we look at it once and say it's in its appropriate spot. So it's going to take O of n time over here. Make sense?
Mm-hmm.
Takes O of n time if we know that it's sorted. That's why insertion sort's so handy. One of the reasons, at least. On the other hand, we end up with this case. 5, 4, 3, 2, 1. So here, we'd have to push 4 down once. Then 3 would have to be... So then we'd get 4, 5. Then 3 would have to get pushed down by 4 and 5. Then 2 would have to be pushed down by 5, 4, 3. And then 1 would have to be pushed down by 5, 4, 3, 2. It's basically, this follows the pattern of 1 plus 2 plus 3 plus 4 plus 5. It follows this pattern, which is equal to n times n minus 1 over 2, which gives us a grand total of O of n time. Sorry, O of n squared time, right? So this is O of n. If it's reversely sorted, that's actually the worst possible case you can get. Okay? Now, what if it's a list of the same n copies of the same number?
Isn't that technically already sorted then?
That is technically already sorted, and I would accept the answer of Wait, no. It is already sorted because insertion sort is a stable sorting algorithm. Okay? Which means that if this was the input, you'd expect them to the same fives if you were keeping track of which 5 was which, right? Then you would be able to like if they were here's a great example. Okay, draw. Okay, 5. So here, draw 5. So if you were given this in the input, you'd expect the colors to appear in exactly the same order as they appeared in the output. So in other words, if this was the input, then this should be the output. Assuming you were sorting by number and not by color. Make sense to people?
Mm-hmm.
That's what a stable algorithm means. That basically the thing that you're sorting by is the only thing you care about, and anything else is going to be maintain the proper order. So, in which case, a list of n copies is considered to be already sorted, so it would be O of n. Okay. So, let's see. I like this question as well over here. So, I'll go back to the other ones, but I'm covering the ones I really like from this one. Suppose you have a hash table and you've inserted some element, right? When you inspect it to see that you see the result is below. Being a good student, you realize this is a problem. So what is the problem? Give a hash function that could cause this behavior, and what is a better hash function? So here's our hash table. What's the issue with it? First off, what strategy is it using for collision resolution?
It's quadratic.
Not quadratic.
Quadratic probing?
Nope, because quadratic probing would mean that basically only one thing would be in a space.
Chaining?
It's using chaining.
Yes, sorry.
No worries.
Oh, the hash function is the last digit times 2.
Yep. So that is the answer to B. The function, and you got that a lot quicker than I did, which is when I first looked at it. The hash function is h of x is equal to
X mod 10 times 2?
X mod 10 times 2, which gives you an index between 0 and 19, which is great, but not great for this. So what is the problem though? Why is this a bad hash function?
No matter how big the array is, you'll only ever get 10 cells being used.
Well, we've got 20 cells, so let's assume that we're only going to use 20 cells. That's plenty for chaining. What's the issue with this hash function?
Well, it doesn't use primes.
Doesn't use primes. What else doesn't it use? It doesn't use any odd indices. Because we're multiplying by 2. So what would be a better hash function? What's a better hash function here?
X mod 10, just by itself?
No, well, we'd still get into the same issue where we have a hash table of size 20 and we're using only half the spots. I'd go with x mod 19 because we're modding by a prime number, and we'd only be missing out on one spot.
Yep.
Creating good hash functions is black magic, and it's beyond the scope of this class as well as a lot of other classes. Let's see what these other ones were. Suppose you have a set of numbers where you look over some constant number of insertions and a linear number of... Okay. Suppose you have a set of numbers where over some time period you do a constant number of insertions. So you add to this set of numbers, and that time the number of things you do is constant, and a linear number of lookups of the maximum. So we look for the biggest item in it a linear number of times. To maintain your set of numbers, you can choose between either a heap or a binary search tree. Assume you are interested in minimizing the average total runtime over a time period. For each structure, what is the asymptotic upper bound on the average runtime case, and which of the two structures should you choose? So here, right, we are having a data structure. We're going to add a constant given number, like maybe 10 items or 20 or 1,000 items to it. But then we're going to do a linear number of lookups of the maximum. So in other words, we're going to look for the biggest item n number of times. Okay? Or, so rather, let's say we are going to insert in n items. Honestly, let's say we insert in n items and we are going to look, and we're going to do k lookups. Okay? And we know that n is orders of magnitude smaller than k. That's really what we're saying. Make sense? Got a constant number of insertions and k number of lookups. So for a binary search tree, what is the total runtime of this? Well, how many insertions do we need to do? We need to do n insertions, and each insertion takes log n time, where n is the number of items in it. And then if we need to find the maximum, okay, if we need to find the maximum, we need to do k number of lookups of the maximum. It says my internet connection is unstable. So we need to do k lookups of the maximum. How long does it take to look up the biggest item in a binary search tree? Anyone? Answer is, it takes log n time. Not log k, because k is the number of lookups we're doing. So that is the runtime for our for a binary search tree. On the other hand, if we use a max heap, it's going to take the same amount of time to build it, but to do a lookup, it's going to just be constant time to look up for the maximum. You just look at the root, so it takes k amount of time. So for this case, you want to use a max heap because because adding something takes the same amount of time, but looking up something is a lot. Looking up the biggest item in a heap is much, much, much quicker. And here it was asking for the average versus the worst case. Honestly, just use the heap. Alright. Are people still hearing me?
Yep.
Okay. Alright. So here's a good theoretical question. Suppose we first insert an element x into a binary search tree that does not already contain x. Then we immediately delete x from the tree. Will the new tree be identical to the original one? If yes, give the reason in no more than 3 sentences. If no, give a counterexample. Draw pictures if you necessary. For reference,
If you necessary.
well, for in fairness, over here, this is from Uppsala University.
Is that Sweden or
yeah,
.se? Ah, yep.
it's Sweden. So English is not the. They're giving the exam in English, but English is not the first language. So, things like that can be that's actually like one of the few issues I've seen here. So,
Yeah, pretty impressive, honestly.
okay. And honestly, that could happen to an English that could happen to somebody very fluent in English if you deem necessary, or basically they could have gone back and rewritten the first part of the sentence and forgotten about the second half.
Yeah.
So, all right, insert an element X into a binary search tree. It doesn't already contain X. Then immediately delete it. Is it the same tree? Will the new tree be identical? Well, first off, if you're a philosophy student, you can argue the ship of Theseus thing, if you really want to. If you replace every board in a ship over time, is it still the same ship at the end? Every molecule in your body gets replaced over the course of 7 years, according to... I don't know if that's true. Is it, Annie?
What?
Every molecule in your body gets replaced over the course of 7 years?
Theoretically.
In theory. Are you still the same person after all those replacements?
That sounds like the kind of fact that just gets shared.
It does sound like the kind of fact that gets shared. Like you only use, 10% of your brain, which is utter horse. But anyway. But for our purposes here, we're not philosophy students. Right? So, by being the same to the original, is it going to be the same looking tree? Okay? Yes or no? Is it going to be the same tree? If you insert an item and immediately delete it.
Yes.
Why?
Because it's going to be inserted into a position that doesn't exist already.
And that position is a what?
It's going to be a leaf.
Yep. And how do you delete a leaf?
You just delete it.
You just delete it. It doesn't adjust the tree at all, right? Example,
Yep.
right? Insert a node. It's going to go into any one of these positions over here. Any one of these positions over here. And then it's immediately going to get deleted. Right? So if we put it over here, or over here, or over here, or over here, doesn't matter. Immediately delete it. It's going to be the same one that doesn't exist. If it's a balanced binary tree, self-bouncing binary search tree, you might have some issues, right? Because it's going to redirect. The only way that inserting is going to that if that happens, the only way to make it change is that basically if you insert items in between when you add it and delete it. Because that will change, that will make it that the node is possibly no longer a leaf node. Okay. So let's see. Oh, I like this one. Because I don't really know the answer to it. Or I don't have a definite answer, I feel. So suppose you have a graph like this one below. From start to goal. The dots signify some part of the graph that you don't know exactly. Not a straight link. In other words, right, we've got multiple paths from the start to the goal. Okay? Multiple ways to get there. Right? But there's not a direct link, right? There's no immediate single edge from start to goal, right? Make sense to everybody?
Yep.
Okay. Actually, I kind of do know this answer. So, however, there's many paths from start to goal. You also know that the paths tend to be rather long. Suppose you want to implement a program that searches for a path and returns the first one it can find. Doesn't need to be finding for optimal in any sense. Just any path will do. Will you want to use BFS or DFS as the basis for your program?
DFS.
DFS. Sorry, which one?
DFS.
Why?
Because it'll go as far as it can until it reaches a dead end, and then backtrack.
Right. So how many? So, what would you say is the portion of the nodes it would hit? What's the worst case? What do you think? How do you feel on average how many nodes it would hit?
Maybe like 10%.
10%, 50% doesn't. But would it hit all the possible edges?
No,
Okay. What about BFS?
that would hit all of them.
That would hit all the possible edges because if we're looking at this graph with the way they've constructed it, it's a what is this? A directed acyclic graph, or not necessarily a directed acyclic graph, but it's a directed graph, and we've got everything that goes from start and everything goes to goal. We don't necessarily know if there's no cycles in it because we could have, start go from, we could have start go to here, which would go to here, which would go to here, which would go to here, and then that would go to here, which would go to here, right? So we could get a cycle, right?
Yeah.
But depth first search would just simply go, okay, I've seen this node for board, backtrack, now go this way. So depth first search would be better for this case. Does that make sense to everybody? Now, if you've got a large network, though, this does get into the I never really. So I'm gonna leave this though. So the last thing for my class, I'm gonna talk about this in relationship to Facebook, and we're gonna go on a wild journey. Okay. So let's go ahead and I'm gonna bring up a fella here. We don't normally get to bring in psychology, but we do. Okay. This guy. Come on, there we go. Stanley Milgram. What is he famous for? He is famous for the Milgram Experiment, a controversial experiment on obedience. You see, he looked at the trial of Adolf Eichmann, who was one of the architects of the Holocaust. So, and he basically, and of course, the common defense of many Nazis when they went on trial was I was just following orders, or I was doing that, I was forced to do that. And so basically he thought, well, is that true? Are people really just jerks who will just follow orders? And so he performed what's currently called the Milgram Experiment, which is one of the biggest and most famous experiments in social psychology. Which simply, and I would look it up and do this. Public announcement will pay you $4 for 1 hour of your time, $4 for 1 hour of your time, which 1960s, that's nice, right? And there's 3 participants in each run of in each session of the experiment. You have the experimenter, who was in charge of the experiment, and then you had the teacher and the learner. The teacher was the volunteer. The teachers were led to believe they were merely assisting in the experiment, whereas they were actually the subject. And the learner was an actor, and he was pretending to be another volunteer. So they randomly would choose roles and for the teacher and the learner, and the volunteer and the person who actually volunteered would be the teacher, and the learner would be the Confederate. And what it would be is that basically that you had to, the actor would always claim to have drawn the slip that read learner, guaranteeing the subject would always be the teacher. Both slips would say teacher. So they rigged it so that no matter what happened, that the person would be the teacher. The teacher and learner were separated such they could communicate but not see each other. And a point prior to the actual test, the teacher was given the sample electrical shock from the electroshock generator in order to experience first hate what the shock that the learner would supposedly receive during the experiment would look like. So the learner is strapped into this electric chair that's going to shock him. And the experimenter tells the participants to ensure the learner is not to escape. And basically, you're supposed to... anytime the learner gave the wrong answer, you were supposed to shock them. And each time it would increment the voltage. And thing is, of course, the learner's not actually getting shocked. He's just an actor. So he's going to be all histrionic and just simply play over the speaker that, ow, I'm being shocked. And so there's a range of shocks, basically, and there would be one labeled death, essentially. And basically, the question is, how far are people going to go before they can halt, before they stop? If at any time the teacher indicated to halt the experiment, the experimenter was supposed to give specific verbal prods in order. Please continue. The experiment requires you continue. It is absolutely essential you must continue, and you have no other choice. You must go on. So here's the question. So so the experiment stops after one of two conditions are met. The maximum 450 volt shock is performed, or if all 4 prompts are used after, if he has to stop after 4 prompts. So 5 times asked to stop, then the experiment is stopped. So the question is, what majority of people administered the 450 volt shock? Or what portion of people? Anyone want to be pessimistic?
Let's say maybe 66%.
All of them.
The results, 65% administered the 450 volt shock, and all administered shocks of at least 300 volts. There is a number of the ethics. Big things happened. Ethics. There's been a lot of there's a troubling mismatch between descriptions and the evidence, and there's been another study that says that person says that they must have manipulated the results, but honestly, people will this has been redone, but people would basically follow the directions, and because they would respect authority. So there's been replications and variations of it, because it's not necessarily the best. Small sample size, drawn from a specific group, not a very diverse group, So it's a very interesting experiment. So why are we talking about this? Well, Milgram is famous for this experiment and one other experiment, which is the small world experiment, which came up with the concept of 6 degrees of separation. And that experiment, basically, it was a mail forwarding experiment. Basically, people in Kansas were told, you need to, if you know this person, send the mail to him. If you don't know this person, this person in Boston, Massachusetts, then send this mail to the person you believe is most likely to know this person. So somebody in Kansas might send it to Iowa, who might send it to Indiana, who might send it to Tennessee, who might send it to Virginia, to New York, and that person in New York might notice. And on average, it took about 6 forwards from this random person in Kansas to get to this other person. And the idea here is actually we find that a lot of networks, a lot of graphs, especially of human relationships, but also of the internet, are what we call small world networks, where you have basically these, not just small world, but what is it? Notice that it goes with social network. But actually, if we look at this social network, you get and there's a lot of studies. As you can see, there's a lot of like visualization of these. It's a scale-free network, where basically a lot of people, basically there's people, where a lot of people tend to know one person who knows a lot of other people. You probably all have that friend who all your friends seem to know, even though you have a mutual friend, but you're not sure how the other person knows that person. And so graphs I find fascinating because they map human relationships. And that's really interesting. And these human relationships aren't necessarily, easy, but the connection of people is actually fairly small. So I find graphs to be actually a very fascinating subject, because of the ability to looking at human relationships, especially with social networks. So anyway, we have about 15 minutes left. Is there any questions we want before we end the session? Anyone?
No.